Hi, and welcome to Geeks for Geeks. Today, we would be discussing the problem insert a node in a binary search tree. So, the problem statement is self explanatory itself. I would talk about the feedback of this problem. This problem is termed here as an easy level problem, but an intermediate, that is the medium level understanding, is needed to solve up this problem. Implementation is little bit on the easier side. Now we would move forward with the very first sample test case. So we are given in the sample test case, we are given the very first binary search tree as 2, 1 and 3. And the node to be inserted here is something as 4. So how we can solve up this problem? So as you know, the binary search tree follows the property for all the nodes that on the right hand side, the values are greater. On the left hand side, the values are smaller. So we would move on that side. Okay, we would move on that side. So we would say the values to be inserted is 4. So we see that 2 is here. So if 2 is here, then a value 4 should lie on its left part, not its right part, because 4 is greater than the root itself. So we should move on the left hand side. So we are moving on the left hand side. Then we have 3. So now 3 and the value is 4, and that 4 value is greater than 3. So we should move on the left hand side. So now we should move on the left hand side. But here it is null. So we can simply make a new node at this point, and we can say that yes, this value is 4 itself, and this would be true. Let us see one more sample test case, which would make more sense. The very next sample test case is something like 2, then it is 1, then it is 3, and then it is 6. So the node to be inserted here is again 4. So we have here 2. So value greater than 2 should be on the left hand side. Now we have 3. 3 and the value is 4. So a value 4 greater than the current value should be there on the right hand side. So we would move on the right hand side. Okay. So now we are moving on 4, and here 6 is already present. Okay. So a value less than 6 should be present on the left hand side. So we go on this side, but we have a null point at this. So we would say that we would make a pointer here. But is this correct? Let us verify it by writing the in order traversal. So in order traversal is nothing but left, root and right. So the value left is 1. The left part of 2 is done. Then the root, that is 2, and then we go to the right hand side. But 3's left part is not visited up till now. 3's left part, if we have visited, then it would be 3. So now 3 is the left is visited, 3 is visited. Now we would go to the right hand side. Now 6 left hand side is not visited up till now, so we would visit it. Then we would visit the root, that is 6. Now root is done, visited, and then the right part does not exist. Now you can see that this is a sorted result. If you want to see this, the in order traversal, 2's left is 1, then we have the root, that is 2, then 3's left is nothing, so we would have 3, then the root itself, and then we have 4. So we have a sorted result up till now. This is also sorted, this is also sorted. So now we can come to the conclusion that if we would stand at the root, if that value is greater than the root, we would move on to the right hand side. If that value is smaller than the root, we would move on the left hand side. If we are able to find the key that we were looking for, then we would simply return, okay, we would simply return nothing. But if we hit a point by moving this, see, let's say we moved here, then we moved here, but we hit a null pointer. So if the element was supposed to be here and we had a null pointer at this point, then the node should be created at that instance. So we would kind of do this only. Okay, so the same idea would be used in the implementation too. We would say whenever we hit a null condition, we would make the node. Okay, we would make the node. The very next thing is, if we hit a point, like if the current node is what, root. So if root dot data, if root's data is less than the given value, okay, root dot data is less than the given value, this value is less than the value we want to insert, then we would go to the right hand side because this side value would be more. So we would go to right. If in the same manner, if root dot is greater, then we would go to left. And if it is same, we won't do anything. So we would have only the condition for left and right, and this would be done. So now let's just sum up everything in the code itself, and this would be fine enough. So I'm more accustomed to root and data as val itself, and this would make more sense. Okay, so I would say if we hit a null condition, then we would make a new node and we would return that. Okay, this is correct. Now we would say one more thing. If the current value is greater than root dash data, okay, then we would move on to the right hand side. Okay, that is root dash data is less than the val itself. So root dash right is equals to insert root dash right comma val itself. Okay, and we would do the again the same thing but inside else if. Okay, here this one would be less. If that value is less, okay, then we would move on to the left hand side. So this would be left and this would be also on the left hand side. At the end we would simply need to return the root. Okay, this seems simple enough. Now let us see this. And yes, we are able to solve up this problem. Now let's talk about the time complexity of this problem. So if you observe, we would be only going on one side, not on both the side. Either we would go on this side, either it can be less, either it can be more, or either it can be equal. If it is equal, we would stop. If it is more, we would go on to the one side. So this is nothing but the height of the binary search tree. And only we are not using an auxiliary space, so the space complexity is big of 1. That's it for today. Thank you and have a nice day.